Really, all the techniques you already know. There's not really a whole lot of new, theory or concepts or anything that we need to discuss. So we'll just do another example, and then next lecture we'll do another example. And by that point, we'll be basically done with diffusion equation. Move on to the wave equation, and you'll see that the wave equation is also not any different. So another example. Whoops, let's do black. All right, time derivative equals 2 spatial derivatives. And now let's add in a forcing function. And let's make this forcing function depend on time. All right. So I could stick a constant in there, and then it would technically depend on space, and we'd have to take the transform of that constant. But in addition, let's throw in a time-dependent function right there. Okay. So we have a heat diffusion with a uniform heat source across the rod that is constant in space but decays in time. And then we have some boundary conditions. And on the left-hand side, we have a Dirichlet condition, but remember that we now have to modify our boundary conditions by adding a comma t in there. This describes the left-hand side for all time. Then we have another condition on the right-hand side. This describes the right-hand side for all values of time. I'm going to make that equal to 1. And then I'm going to have an initial condition, which is time t equals 0 for all values of x, is given by the function 2x squared minus 1. Okay, and so this is a fully defined diffusion equation. All right, now, anytime we're doing one of these problems, I'm gonna ask some repetitive, redundant, pedantic questions. The method we're going to use to solve this problem can be described by one word, which starts with a T. We're going to use a
transform.
Yes, we're going to use a transform. And just like in chapter 2 and chapter 3, we know that transforms what? What feature of this problem do we see that should raise a red flag if we're talking about solving using transforms?
Maybe the time-dependent part of it?
Nope.
Non-homogeneous boundary conditions.
Non-homogeneous boundary conditions, all right? Transforms do not play well with non-homogeneous boundary conditions, just like 13-year-olds don't play well with 7-year-olds if there's a cat involved. All right, so we need to separate them, and the way we separate them is by constructing a boundary solution. Now, before we get started, before we do all this, what is the spatial operator in this problem? Our whole approach is, even when we introduce time derivatives, to sort of focus on the spatial operator for our solution strategy. So in this problem, what's the spatial operator? Second derivative of x, okay? The spatial operator is the second derivative. All right, and so if we're going to do boundary solution, what must be true of that solution, and what would we like to be true?
No, we would like it to equal 0,
What is it? We'd like it to equal 0.
the boundary solution.
The solution itself to be 0? We would like ubxx to equal 0. More sort of pedantically, we would like L of ub, which in this problem happens to equal ubxx to equal 0. And then what absolutely must be true if we want to call this a boundary solution? This is desirable, but what is like essential? It satisfies these non-homogeneous boundary conditions. All right. So we want u, b. Now note that this right here does not have a time derivative. It doesn't have any time dependence. And so really the boundary solution in this problem will not depend on time. Nevertheless, I'll just, for consistency, I'll write ub of 0, comma, t equals -1 ub of 1, comma, t equals 1. All right. And now I want to solve this. All right. And so if ubxx equals 0, then ub is going to be ax plus b. If you really want it to be precise, and let me go ahead and do this, since it'll show up in another problem that we'll do next time. These are partial derivatives in x. If I'm undoing partial derivatives in x, I no longer necessarily get integration constants. I get functions of t. When I do basically like a partial integration, okay, I'm undoing a partial derivative by taking an integral in x. But the most general function that will go to 0 when I take two x derivatives of it is in fact this structure right here where a and b are now functions of time. Okay. And now I satisfy my boundary conditions, and let's just be precise here too. That makes this a function of x and t. Now I have my first boundary condition, 0 of t. And when x equals 0, that's going to be b of t. And that has to equal -1. So in this case, even though in principle this can depend on time, the boundary conditions are such that this is just a constant. But what if I had said, don't write this down, don't change this. But if, for example, I had said this were equal to -t, then this could be -t, and b of t would be a function of t. All right, and so we'll do an example next time where we do have time-dependent boundary conditions. For now, I just want to point that out, and we'll proceed with the problem as it's written. Okay, our other boundary condition is ub of 1, comma, t, and that is going to be a of t times 1 minus 1, and that's going to equal 1. And so therefore a is 2 and b is -1, and so ub of x comma t is going to be 2x minus 1. Okay, and that does satisfy the boundary conditions. -1 plus 2x, we'll take this from -1 to 1 over the course of x going from 0 to 1, and so we satisfy both this LU boundary equals 0 and the boundary conditions, and so that all checks out. All right, so now what? We have removed the non-homogeneous boundary conditions. Let's figure out the interior problem. And the way we do that is we insert u equals ub plus ui into the original governing equation, okay? And so we get u b t plus ui t equals u b xx plus u I xx plus 10 e to the minus t, where u b of x 0 plus u I of x 0 equals -1 u b, oh sorry, that should be 0 comma t and 0 comma t plus ui of 1 comma t equals 1, and u b of x 0 plus ui of x 0 equals, what was our initial condition? 2x squared minus 1. I see a question over there. Will the initial condition only show up in the interior part? That is a good question, and the answer is yes, because there is no time derivative here. We cannot impose an initial condition on it. The only reason we have an initial condition is the time derivative in the original problem. Since the boundary solution is purely a spatial problem, it has no initial condition. But that is an excellent question, and it is worth stating that explicitly. So I will do that, and I will post these. I've posted a couple of the lectures. I'll post this one as well. No initial condition. Very good question. Okay, so here's our interior problem. What can we simplify? List things that we can simplify or cancel. Go in the group chat. I should like keep score and give like, but I'll never see any of you again. So there's like no way to give prizes. U xx equals 0. Which u, yes, u b xx equals 0. Why? Because we said so. Excellent. Yes, u b xx equals 0. What else? What else can I simplify? The ub 0t and -1. Yes, ub of 0t equals -1 because we said so. What else? ub 1t and 1. Excellent. Because we said so. Now, I haven't completely, that's all the typical things that we cross out, but I still have 2 instances of u boundary remaining. What do I do with those? What do I do with this? And what do I do with this? Excellent. Just plug in u boundary. We know u boundary. They go away. Do they? I will say, we know u boundary. We solved for u boundary already. And so we can simply take it and insert it into these 2 expressions. This expression says, take the time derivative of u boundary. And it so happens that the time derivative of this equals 0. Note that this is not a necessary outcome. This does not happen always, or because we said so. It happens because the boundary conditions for the boundary solution did not have a time dependence. And so the boundary solution did not have a time dependence. But if our boundary conditions had a time dependence, then the boundary solution would have had a time dependence, and we would have gotten some time dependent function here when we took the derivative. Okay? Now that is not happening in this problem. I wanted to start with, a little bit more complicated than last time before going to full complexity. Next example we'll do will have time dependent boundary conditions, and we will not get 0 here. Okay? But in this particular problem, we do get 0 here for ub, the time derivative of ub. What about this? Does that disappear? Does that Does that cancel this by symmetry? We canceled here, so we cancel here. No, I'm just playing with you. No, we know U boundary. We plug it in. UB of x when t equals 0 is just 2x minus 1. And so in order to formulate the interior problem, we're going to have to subtract this from both sides of that initial condition. And if this had been non-zero, we would have had to subtract it from both sides of the original governing PDE. Okay? So in any case, what we get for our interior problem is ui sub t equals uixx plus 10 e to the minus t. Ui of 0, t equals 0. Ui of 1, comma, t equals 0. There's our homogeneous boundary conditions. And our new revised initial condition, x0 is going to be 2x squared minus 1 minus 2x plus 1, okay, which is going to be 2x squared minus 2x. And if you wanted to give this a name, okay, you could say, well, this is our initial condition, I of x. And if I were giving things names, I would say this is a modified initial condition, I tilde of x. It's not exactly the same initial condition as the original problem, all right, which is kind of notable, which is why I'm noting it. But nevertheless, you know, it's some initial condition, and we have an interior problem with homogeneous boundary conditions and some initial condition. We can proceed from here. Okay, that's our interior problem. How are we going to solve the interior problem again? Eigenfunctions. So how do we find the eigenfunctions? What equation do the eigenfunctions satisfy? All right, I went to the trouble of identifying the operator right here at the beginning. This is the spatial operator. And so having identified that, I can immediately write down that the eigenfunctions satisfy L phi equals minus lambda phi, just like every other problem we've done, with the same boundary conditions as the interior problem. Phi of 0 equals 0 and phi of 1 equals 0. Eigenfunctions are purely spatial. They have no time dependence, and so they have no t argument here. This is exactly like we did before. And in fact, this problem is the very first problem we ever studied, and it's the same set of eigenfunctions that we saw in our last example. Okay, so the next example that I do with the time-dependent boundary conditions, I also need to mix up the problem a little bit so that we get a different set of eigenfunctions. But anyway, we've seen this set of eigenfunctions before. Lambda sub n is n pi quantity squared, and phi sub n of x is sine n pi x. By the way, if this happens, say on a test, oh, and I need to talk about that. If you see an operator and you absolutely know 100% what the eigenfunctions for that operator are, you may just write them down. Okay. Yes, I'm doing this partly to save time, but I'm not just trying to create busy work for you. So if you encounter a problem and you say, oh, I know this, I've seen these eigenfunctions before, just say that. We have seen this operator before in class, and its eigenvalues and eigenfunctions are blank. And that is perfectly acceptable in this class. Okay, and so with this set of eigenvalues and eigenfunctions, we know that the transform is 2 integral from 0 to 1 of whatever we're transforming times sine n pi x dx. and that the inverse transform to recover the original thing is the sum n goes from 1 to infinity of box of n sine n pi dx. What's the weight function here? Why didn't I talk about a weight function? Is this not a Sturm-Liouville problem? Why didn't I do that? No. We don't divide by lambda n as a part of the transform inverse transform. After we take the transform, then there'll be a solution step that will involve, in fact, it won't. It only, the solution is only to divide by lambda n in the case of boundary value problems. Now that we have time derivatives, instead of an algebra problem when we take the transform, we're going to get a differential equation. And so instead of just simply dividing by lambda, we're going to have to solve that ODE. All right, the answer is it is a Sturm-Liouville problem. It's just that the weight function is 1. Okay, there is no first derivative term. And so if we said, hang on a second, I think there's something about Sturm-Liouville form here. I would say, all right, I take my second derivative and first derivative terms, but I don't have any first derivative terms. And so in order to find that weight function, I would say the derivative of this, oh wait, no. The derivative of this has to equal this, which gives me w prime equals 0, or w equals a constant. And since any multiple of a weight function is still a valid weight function, we find that the weight function is just 1. All right, so you could say this is already in Sturm-Liouville form with weight function 1, which is why I didn't say anything about any of that. All right, so now we're ready to actually take the transform. All right, and I have ut. I need to take its transform. Then I have uxx. I need to take its transform. 10 e to the minus t. I need to take its transform. Is there anything else I need to take the transform of? Remember, the transform gets rid of all the x's and replaces them with n. So anything that in principle depends on x, even if it doesn't have an x written in it, you have to take the transform and convert that spatial dependence into a dependence on the index n. So what else in this problem depends on space?
That one boundary term.
It's not a boundary term. At least we don't call it a boundary term.
The spatial dependence?
We call it an initial condition, right?
Okay.
You're thinking about this right here, which is the modified initial condition. All right. So, oh, and I forgot to note that this is the interior solution. And so that last thing is my, I have my initial condition. I have ui of x0. I have to take the transform of that. And then it is, what was it? 2x squared minus 2x. Okay. So I have to figure out what all 5 of these things mean. Now, what is the transform of uixx? It would be an integral, yes. We would do the integral of uixx times sine n pi x from 0 to 1 times 2. But since we're taking here the transform of a self-adjoint operator, we know, we've proved that in general, this equals minus lambda sub n u sub n. Okay, that was true in chapter 2 and chapter 3, and it remains true here in chapter 4. This is a spatial operator, a self-adjoint spatial operator, and we're taking the spatial transform, and so this continues to be minus lambda sub n u sub n. Indeed, this is the primary benefit of the transform approach, is that it takes away the spatial derivatives and replaces them with multiplication by a constant, and that's going to turn this partial differential equation into an ordinary differential equation. All right. Now, what did we say happens to this term? The transform of the time derivative. Remember that the transform mathematically is an integral in x. So here I have the integral in x of the time derivative. How can I manipulate that? I can switch the order of operations, time derivative of the transform. I'll just take a minute to say I'm happy. I'd love to see a few more people participating in the group chat. Otherwise, I know this can get kind of isolating because we can't actually see each other. I see that there are 3 or 4 of you that are, confident and happy to participate. I'd love for some other people to step up and chip in the group chat. But yes, we can interchange the order of operations, and that can become the time derivative of u sub n. Okay. What about this term? The x integral of an evaluation at t equals 0. How can we manipulate this into a more friendly form? What did we do last time? This says first evaluate at t equals 0, then take the transform in x. But since x and t are independent variables, yeah, close, if you stick a u in there. First, take the transform, then evaluate at t equals 0. Okay, so all that's left is to, we have to calculate this, right? And then we have to calculate this. Okay, so let's do that on the next page. And let me start with the one on the left. Okay, what is 10 e to the minus t n? And I just want to point something out here. It's an integral. First of all, we're going to have to calculate it. We're going to have to do an integral. To integral from 0 to 1, 10 e to the minus t times sine n pi x dx. But do you notice anything about this? Is there anything you can do to this integral to simplify it?
We have that e to the negative t term. Perhaps we could move that out.
Perhaps what?
We could move that out.
That's right. So this term right here does not depend on time. It can be pulled outside the integral. As far as x is concerned, the integration variable, this is just a constant, and constants can be pulled outside of the integral. So I'll just note that this can be written e to the minus t. In fact, we could also pull this 10 out, right? Times 2 integral from 0 to 1 of 1 times sine n pi x dx. So what I want to note all right, this is not necessarily critical, but it can save you some notation, is that this right here can also be written equals 10 e to the minus t times the transform of 1. Okay? Now you can't get rid of the transform entirely because you still have to take the transform and do the integral of something times sine n pi x. It would be tempting to just say, oh, well, that is just equal to 10 e to the minus t. And that is wrong, okay? You're still doing the transform of something, but you can simplify what's inside of that to just be 1, right? And write this in your ODE notation is just saying, well, here's some constant, but it's multiplying this 10 e to the minus t. Okay, so what is the transform of 1? Let's proceed. Okay, yeah, that's fine. We're in the middle of the calculation. We can do it. Okay, so we've got 10 e to the minus t times, and then we're going to have a 2, and then we're going to have a integral of sine is negative cosine n pi x over n pi from 0 to 1, which is 20 e to the minus t 1 minus cosine of n pi divided by n pi. All right, but it's still, as we go through the calculation, it's worth remembering that is equal to this quantity right here. So I don't have to keep rewriting this. All right, let's go ahead and calculate the other thing now. This is a little bit more conventional. It was 2x squared minus 2x, the transform of that, right? Which is going to give us 2 integral from 0 to 1 of 2x squared minus 2x times sine of n pi x dx. And mathematically, I'm going to use my integration by parts chart because that's second order polynomial times a sine function. Okay, and so I'm going to pull that 2 inside for the purposes of calculating. That means the thing I'm going to be differentiating is 4x squared minus 4x. Its derivative is 8x minus 4. Its derivative is 8, and its derivative is 0. The thing I'm going to be integrating is sine n pi x. Its integral is negative cosine n pi x over n pi. Its integral is negative sine n pi x over n pi quantity squared, and its integral is cosine n pi x over n pi quantity cubed. And I've got a product and a product and a product, plus, minus, plus, minus. Okay, and so what is that going to give me? I'm going to not write down some things that I can already identify will be 0. This quantity here is going to be 0 at both x equals 0, obviously, and at x equals 1. Okay, and so I'm not going to get anything from this product. Similarly, sine n pi x is 0 at both at x equals 0 and at x equals 1. So I'm not going to get anything here. That's convenient. It simplifies my life a little bit. That means the integral is going to be 8 over n pi quantity cubed times cosine n pi x evaluated from 0 to 1. That is going to be cosine n pi minus 1. Okay, so here is, the transforms of the things I actually need to calculate. And now I'm going to put all that back together. I've got one more thing I need to do.
Could you go over how you were able to get rid of a lot of the terms in that part chart again?
Sure. Okay, remember, after I compute the integral, I'm going to evaluate it at 0 and 1, right? So sine n pi x is a big giveaway because sine of 0 is 0 and sine of n pi is 0. Those are the roots of sine. Okay, so I know this term is going to be 0 on both sides, which means I don't need to worry about this product. Similarly, okay, cosine is not 0 on both sides, but this happens to be 0 on both sides. We kind of got lucky there, all right? Because at 0, I get 0, obviously, and at 1, I get 4 minus 4 is 0. So because this is 0 on both sides, this product does not contribute to my integral as well. So the only term that contributes is going to be this one, and it gives me this term here.
Sweet, thank you.
Yep. Okay, so my resulting transform PDE, I get an ODE, I get dun dt plus lambda sub n u sub n equals, and I'm just going to, for simplicity, to help me solve the ODE, I'm going to write this as 10 e to the minus t, or maybe just, that's fine. 10 times 1n e to the minus t, or you could write 10n. It's just that I went to the trouble of making it equal to 1n up there, so I'll stay consistent with that. With uin of 0, these should be i's, equal that, whatever that is, okay? So yeah, I went and calculated these things, and I had to do that. But the new thing that arises when I solve diffusion, everything we've done so far has been exactly like what we did in boundary value problems, chapter 2 and chapter 3. The one new thing is that when we take the transform, instead of getting an algebra equation, okay, which would give me just divide by lambda to get the solution, I now get an ordinary differential equation. And so the one new thing I have to do in all of this is solve this ODE. Okay, how do I solve this ODE? Because we're sort of running out of time, I won't make you answer any questions. I'll just sort of do it. I need to find a homogeneous solution and a particular solution. I see that this is a constant coefficient ODE, and so my homogeneous solution is going to be, I can guess. I'm going to guess e to the RT. Remember, this is now a time-dependent ODE, and so we're guessing solutions in time. That's a little bit different than when we're finding eigenfunctions. We're guessing spatial solutions. Okay, so I guess e to the RT. I plug that in. I get R plus lambda sub n equals 0. R equals minus lambda sub n. UH of t equals C1 e to the minus lambda sub n t. Okay, but what about my particular solution? Again, it's constant coefficient, and so the answer is often guess, okay? And what do we call guessing the particular solution when I have constant coefficients? We call that undetermined coefficients. And in the method of undetermined coefficients, I guess basically what I'm given. So I'm going to guess a e to the minus t, right? This is method of undetermined coefficients. And if I plug that in, I get the derivative is going to be negative a e to the minus t plus lambda sub n a e to the minus t equals 10 times 1 sub n e to the minus t. And the coefficients of these e to the minus t's have to be equal for me to claim that I have found a solution. And what that tells me is that a times lambda sub n minus 1 equals 10 times 1 sub n. And so a equals 10 times 1 sub n over lambda sub n minus 1. And so the particular solution is 10 1 sub n over lambda minus 1 e to the minus t. And this is fine as long as none of the lambdas equal 1. That is, as long as none of the coefficients here give us a homogeneous solution equal to the forcing function, right? Which was kind of the one big thing you had to worry about in the method of undetermined coefficients, which is the reason I'm not a huge fan of the method of undetermined coefficients. But in this case, none of our lambdas are equal to 1. The lambdas are all n pi squared, and none of those are 1. And so we're fine. So our general solution is 10. I just want to write 10 sub n. I really, really want to do that. Next time I teach the class, I won't move the 10 outside of the integral. Over lambda sub n minus 1 e to the minus t plus c1 e to the minus lambda sub n t. Yes, just a second. And then I satisfy my initial condition, uin of 0. Well, when t equals 0, these exponents are just 1. So I get 10 times 1 sub n over lambda sub n minus 1 plus c1, and that has to equal my transformed initial condition, which is 2x squared minus 2x sub n. And so therefore, c1 equals that minus that, and uin of t equals 10 times 1 sub n over lambda sub n minus 1 e to the minus t minus 1 plus 2x squared minus 2x sub n. E to the minus t. Okay, previous page. Yes. You just want to see it, or do you have a question? It's fine if you just want to see it.
I just wanted to see it.
Okay.
Didn't quite finish writing down that last part. Okay, I'm good.
Okay. All right. So finally, we had this extra step, right? And remember I said, anytime we have to solve an ODE, just imagine that you're sort of going downstairs into the basement, and you might have to be down there for a while to solve the ODE because ODEs are not necessarily easy. All right. Don't get distracted by the amount of work it was to solve this ODE from the general flow of what we're doing here. We take the transform of the problem, okay? And we get a simpler problem. Then we solve the simpler problem. And finally, we take the inverse transform. So I took the transform of a PDE and I got an ODE. And then I have to go in the basement and I have to work to solve my ODEs. And now I have a solution to my ODE. And the last step is to take the inverse transform. Questions. Why is it not e to the minus lambda n t on the final equation you wrote? Because, you're right. You're right. Thank you. Because I was thinking of something else. I was thinking of a previous problem I had done. The reason I wrote it in this form is because I like to group the effect of the initial condition in one term and the effect of the forcing function in another term. This is entirely due to the forcing function. This is entirely due to the initial condition. And I like to be able to separate those two things. Okay, anyway, finally, the last step is to invert this problem. And we're out of time, so let me just write down. Okay, final solution. I have my boundary solution, which was 2x minus 1. And then I had my interior solution, which is all of this times sine n pi x added up and from 1 to infinity. And I'll finish. You can leave if you've got somewhere to be. Otherwise, I'll finish up with a 1-minute movie. All right. Here is the movie solution of that equation. Okay. I start with my forcing function is decaying in time. It starts off with a heat source. And so initially you see this pulse of heat as heat is being pumped into the bar everywhere before flowing out, initially both sides and then the left side. But then as time evolves, my forcing function goes to 0. And if I have no forcing, then the heat equation moves toward a long-term steady state that looks like a straight line connecting -1 and 1. And that's what we see this solution doing. All right, so I have a solution that kind of changes direction in the middle because of the forcing function going to 0. So as usual, yeah, it's fine. Like once, is it okay to write it out like this? If at one time you have written out the transformed solution, then by all means, you don't have to keep copying it over and over again. When you write down your final solution, you can do that. I would only ask that this be like close to this, okay? So that I don't have to go like hunting through your work to figure out where you defined this thing. So yeah. Are we doing tests after all? So I was talking to some of the other faculty, and the solution they have hit upon for tests is, I know, I'm so sorry, is to do kind of like what you described with that creepy company run by college students. I just hope it's like less creepy if it's not some random college student on the internet. I have one person who's not a fan, but that seems to be what everybody in the math department is doing, is just having everybody turn on your cameras and then take a time test, just like we would if we were in person.
Do you know the name of the program?
What program?
The proctoring service?
Zoom, like just Zoom.
Oh, do it on Zoom. Okay.
Just like we are here. Like we're all logged in. I would ask you to turn on your cameras, and then we would all just be, sitting down. Yeah, I know. But it's not really any different than a test. I would love to consider take-home tests. Yeah, it would be me. It would not be some random person. I would love to consider take-home tests. I just have to say I have tried take-home tests like 3 or 4 times, and every single time I've had problems with students seeking unauthorized help. And so like every time, 95% of the students are fine. It's like really a matter of the small number of people like ruining it for everyone else. But I've like never successfully given a take-home test where that didn't happen. Yeah, definitely not interested in farming this off to some random people. Exam 2 date. Like I always promise to give at least a week. I would put forward the idea that we just follow the original plan, which is Thursday nights, which means you have a little bit more time. And so I would sort of propose like a week from now, next Thursday. I know that's not quite a week, but too much longer than that, and we're like running out of time. And then I guess we've basically finished the diffusion equation, so I would say over chapters 3 and 4. You know what? No. Oh, that's a fascinating question. Same thing. If you can't do Thursday nights, we'll work something out. Exactly like if we were all still on campus. I will even be willing to say open notes as like a compensatory thing. Like, I'm sorry, I know this isn't optimal, so open notes. I still highly encourage you to make a 1-page formula sheet. The very process of making that formula sheet is often more useful than the formula sheet itself. So don't take the fact that it's open notes as a reason not to make a 1-page formula sheet. You know, otherwise you'll sort of spend more time paging through your notes than if you had just made the formula sheet. As far as turning it in, I'll have to think about that. I'm guessing just Canvas, you know, take, yeah, you'll have to figure out something about the printer. I know, I'm sorry. Chapters 3 and 4 are Sturm-Liouville problems, and the ones we've just finished are initial value problems in time, PDEs. What else? As far as turning it in, I would say, you know, print it off, do it, and then take pictures of it with your phone and just upload it to Canvas. Multiple choice Canvas test. Yeah, sorry. Are we going to have a chapter 4? Have I not assigned a chapter 4 homework? Oh man. Okay. Then yes, I will assign a chapter 4 homework right now. And I'm thinking, if I haven't assigned the homework yet, then Thursday seems a little bit early. I might, answers to chapter 3. Yes, I'll put that on my to-do list. Blank paper's fine if you don't have a printer. It doesn't take very long to write the problems down. You can, you know, pull up the problems on your computer. Thursday after next. Oh, you guys are killing me. Yeah, okay. Tuesday, that's a good compromise. How about Tuesday? Okay. All right. Well, I know. I'm sorry. I mean, different people have different things. Some on Tuesdays, some on Thursdays. But if you have something on Tuesdays, you know, contact me and we'll work something out, just like we did for the Thursday people last time. So all right, let's plan on that. Let's plan on that Tuesday. I will give you homework today. I will post chapter 3 answers today. No, not upcoming Tuesday. It's like a week from the next Tuesday. So yeah, the 14th. Will we have the final in the same format? I guess. I gotta admit, I'm kind of making this up as I go along. I will probably confer with other faculty on the format of the final, and you know, we'll just have to figure that out. I would love it how important the final is. I just don't think we're going to be back on campus by May. So I would expect all further tests, you know, to be in some sort of weird compromise online format like this. And we'll just have to figure it out. And you guys all got the message. I know it came out from the whole university about the new grading policy, right? So I will attempt to assign grades like normal, and then you will have the option of choosing at your discretion whether to accept the grade or convert that to an S or an S minus or no credit. Just to clarify, chapter 3 and 4 are, chapter 3 is the new operator, Sturm-Liouville form, the whole weight function thing. Chapter 4 is the diffusion equation. And then chapter 5 will be the wave equation. So we did chapters 1 and 2 on the last test. And we'll do chapters 3 and 4 on this one in a week and a half. Easier questions. I'll see what I can do. I'll see what I can do. I was going to ask, do you mean on the final or on the next test? But I anticipated that your response would simply be yes. Okay. If anyone else has more questions, feel free to hang around. If you want to ask a question about the example we did, that's fine. If there's something you didn't have time to write down, again, I will post these, post notes. What day is the homework going to be due? Let's say it should be before the exam. Why don't we say Friday, a week from today? I'll post it today. Do the homework due Friday, and I will do a review. Yep. Just like last time, I'll do a review. That's part of the compensation for having evening exams. I'll probably do that on maybe say Friday, so that it's not just right the day before. If I give it to you on Friday, then you have a couple of days to think about it over the weekend as you finish getting ready. No class on April 10th. Oh, it's Good Friday. Okay. Then Monday, probably. Due Monday. I guess it could be due Monday. There's no reason it can't be due on Monday. And then if we do the review Monday, that works. Yeah, the 13th. And then what I'll also do is I'll have like extended extra office hours on the morning and early afternoon of Tuesday the 14th, so that I'll give you the review. You'll do the homework. I'll give you the review on Monday. You can think about it Monday afternoon, and then Tuesday morning and early afternoon, if you have any questions, you can come ask them in virtual office hours. No problem. All right. Yes. 2 weeks of quarantine learning concluded. You guys have a good weekend too. Stay safe, and we'll see you next week.
Have fun.
Yep.